So what is electromagnetic induction? Let's have a look at the words. Induction, if you look this up in the dictionary, it means to bring about or to cause. Magnetic must be something to do with magnets. Electro, electricity. So it means to bring about or to cause electricity using a magnet. Let's see how that works. So here we have a magnet, a wire, and a meter to measure the current that's produced. This is a strong magnet. I need to take off the iron keeper, and I need to plug my wire into the milliammeter. So all we have is a wire, a magnet, and a milliammeter. So if we move the wire up and down through the magnetic field between the two poles, we see from the meter that we get a very slight deflection. So how do we make the current bigger? Well, if one wire produces that small current, what will two do? If I take the wire and I coil it, and I put two through, slightly more. Let's try it with 3, 4, 5, and now you can see we're getting a much bigger current. If I do even more than that, I move that through the magnet, now we're getting a much bigger current. And so using a coil in a magnet induces a much bigger voltage and therefore current. Let's have a look at the current more closely. If I move the wires down, you'll notice it deflects one way, and if I move it up, it deflects the other way. So by moving it up and down like this, I'm making current that's going backwards and forwards, so I'm generating alternating current. The other thing to notice is what happens when I vary the speed. If I move it slowly, you can see deflection isn't very large. However, if I move it quickly, we get a much bigger deflection. And finally, notice when I hold it stationary, there's no deflection at all. So the key thing here is there must be movement of the coil through the magnetic field. But what happens if I keep the coil stationary and I move the magnet? I bring the clamp in, so I can clamp the coil, and then see what happens if I keep the coil stationary, but this time I move the magnet. So whether it's the coil moving or the magnet moving, what's happening is the coil is cutting through the magnetic field. Difficult to understand because we can't actually see the magnetic field. So one way that we know how we can see a magnetic field is to put iron filings on a card over the magnet. And here you now see, between the two poles of the magnet, we have these straight magnetic field lines. And it's those field lines we cut through with our wire. I want to go inside and show you a model of this using some laser light. So if you look at the red laser light, this will be representing the magnetic field. If I now introduce the wire, which is fluorescing so we can see it, when it cuts through the magnetic field lines, that's when you get electromagnetic induction occurring. If I hold it stationary, it's no longer cutting through the field lines, and so no electromagnetic induction occurs. Cutting through, that's when we get the induced voltage. And the faster we cut through, the greater the induced voltage. So far we've looked at generating current through linear motion, moving backwards and forwards, but in real life it's done through rotation. Here we have a dynamo, and by rotating the magnet next to the coil, we are generating current. So how does this work? Well, let's have a look at a model. Here I have two boxes to represent the poles of my magnet, my north pole and my south pole. And between those, I have my coil of wire. Now remember, the magnetic field lines go from the north to the south. So if you imagine the field lines going across through the coil. Now as I rotate the coil, this side of the coil is going to be moving up through the field lines, and this side is going to be moving down through the field lines. So they are cutting through the magnetic field as it rotates. So we know that if we have a wire that moves up, the direction of the induced current is different to the wire that moves down. And so what we do is we get a current being induced that goes round the coil, and then that can then go out of the connections at the end. So by rotating a coil inside a magnetic field, we can generate electric current. So we've looked at the model, let's now look and see what happens inside the dynamo. If I look at this, take the end off, you can see that we've got the two curved magnetic pole pieces here and here, and inside we've got not just one coil but 4 coils. If I just take this out, you can see more clearly. There you have the north and the south curved pole pieces, and here we have the 4 different coils. These will be wrapped around an iron core to increase the magnetic effect, and then at the end we have the 2 brushes, the contacts, that carry the current out of the generator. And so through rotatory motion we now generate a current, all through electromagnetic induction. So in conclusion, electromagnetic induction is the production of electricity using magnetism. So all we need is a magnet and a coil. And we need relative motion, either the coil moving in the magnetic field or the magnetic field moving through the coil. And in real generators, we do that through rotatory motion, and we spin the coil inside the magnet, or we spin the magnet inside the coil, and that generates the current that we use.